Jean-Pierre, for the very kind introductions. First of all, I'd like to thank the organizing committee of this wonderful symposium sponsored by the Wright family. And it is my great honor and pleasure to be here to give a talk about what we have been done for the last few years. As you can see from the title of this talk, I'm talking about material based on water. So the title today is Aqua Material. And someday, if your friend visits you and say that this could be the final droplet of an oil on the earth, what you can do? Well, the oil result is finite. So what we have to do is to invent something that can contribute the deceleration of the consumption of oil. Here. Otherwise, the oil is gone. So nowadays, we very much depend on oils for making petrochemicals. And we get used to petrochemicals usage. So if there's no oil, then we can't survive. So this could be the final day of human beings and also on the earth. So one of the scientists working in the 21st century, we have to think about how we are able to decelerate consumption of oils. Well, this is one of my messages today. So I'm talking about water. Water is one of two representative liquids on the earth. Water is recyclable and ubiquitous. And that covers 70% of the surface of a planet. And they constitute 60% of a body. So water is very, very essential for human beings and animals and plants. Because of the shortage of possible shortage of water in the future, why don't you use water as a source of making materials? Water is very special because water molecules in water are hydrogen bonded, so they are connected together. As a consequence of this, the motion of water is highly congested. Its molecular mass is only 18, but it boils at 100 degrees Celsius. Compared with other organic molecules of the comparable molecular weight or even higher, the boiling point is higher than those of organic molecules because the water molecules are hydrogen bonded. So everybody knows water has three states. Steam is for gas, and water is a liquid state, and ice is in the solid states. And today, I'd like to introduce one more state, which is aqua material. I'm afraid I must receive some criticism from physicists, but today I'd like to tell a bit about aqua materials. Aqua materials behave like quasi-solid or quasi-liquid, depending on the environment conditions. And in our daily life, you see many water-based materials which we call hydrogels. In foods, you see many and soft contact lens, toothpaste, ketchup, and there are many examples in living organisms, including us. So hydrogels are very, very important in our daily life. But in some sense, those hydrogels are very weak. So no one can expect that hydrogels can work for structural materials. So the question here is how we are able to make rather strong hydrogels. So there are many challenges here because what we can do is to use molecules. But what we are requested is to make a very strong 3D-dimensional network structure like this, and that traps water molecules, and the system becomes gel. But even when the three-dimensional network is very strong, but if this is just a very small fragment, we are not able to realize high mechanical properties. The three-dimensional network structures has to be developed over a macroscopic length scale. Otherwise, we are not able to make strong materials. So that's why here we have a very big challenge because we have no idea how we are able to make such a very well-developed, strong, three-dimensional network structure by using molecules. So this is the material we fabricated, and because it contains a very minute amount of organic molecules, so we dare to call these materials aqua materials, not hydrogels. So it is mostly composed of water that can be processed into self-standing objects of any shapes, like plastics. It is elastic, like this. And again, it contains only a very minute amount of organic molecules. So we hope that it contributes to the sustainable society because of the outer low dependency on fossil fuels. So those people that are involved in this project, I'd like to introduce three people, Dr. Wan, Justin Miner, and Okulo. Those are main players for developing this unique type of hydrogel. So all chemists have a library of their own molecules, and this is one of some of the molecules in the molecular toolbox. And initially, we did not expect that we are able to make such hydrogels. This is just a coincidence. And a few years ago, we started a new project, biointerface, featuring a unique type of macromolecule called dendrimers. Here. So this is the molecule we prepared, designed for making connection of biological phenomena with chemistry. So this molecule is totally water-soluble, having quite a few number of guanidinium ions on the periphery of these molecules. Dendrimer is a very unique type of macromolecules. Usually, it adopts a global shape. So if you talk about polymers, then usually you consider that polymer is a linear molecules. But dendrimer is a well-defined hyperbranched molecules starting from core units with functional surface units. So this is the graphical cartoon of dendrimers. And we have very regular branch structures starting from core unit. And then if you just increase the generation number, then you can increase the number of branch unit and the periphery. And this structure is very, very important because it is very well defined and has a certain well-defined molecular weights and the very well-defined structures. So we are very much fascinated by these molecules. And for this particular purpose, we decided to make water-soluble dendrimers and investigated its biological functions. Once again, what you see here is the water dendritic molecules we synthesize, and the key motif is guanidinium ions that are located on the exterior surface of the dendrimers. This is not the big dendrimers, but it works. So this is a guanidinium ions because this unit is known to do a very interesting chemistry in water. So here we have guanidinium ions and the counterpart, oxyanion, that present ubiquitously on the surface of proteins and biomacromolecules. So we chose guanidinium ions because it is known to interact with oxyanion and the proteins and nucleic acid surface initially by plus-minus electrostatic interactions. Then they form hydrogen bonds. So because of these double interactions, so-called salt bridge, sorry, we don't see the upper part, salt bridge. So this is one of the strongest interactions that potentially can work in water. But if you consider that we're going to utilize these molecules in a body, so there are many salts that compete with interactions. So we need to amplify these interactions. That's why we utilize dendrimers, because dendrimer can adapt many numbers of guanidinium ions on the surface of the molecule. So consider that this is like a molecular octopus. So octopus has 8 legs. That's why it is very difficult to take it out. But if octopus has only 1 leg, it is easy to take it out. So on the basis of this concept, we just decolate the dendrimer's surface with guanidinium ions as a sticky part. So I'd like to tell you two demonstrations how this molecule can work under physiological conditions in our body. Okay? So an actomyosin is known as a hybrid of actin and myosin. It's a so-called biomolecular machines. And it is known that if you add an ATP, is an energetic molecule, then actomyosin start to move. So that's why we call this as biomolecular machines. But by certain technique, you are able to extract actin to form actin filaments here. These are actin filaments. And we just put actin filaments on the surface of the glass, decorated with myosin part. Myosin here. Then we have hybrid structures, which is different from the biological system, but they interact with one another. Then what happens if you add ATP? So they start to move on the glass surface. So this is a live video, and you can see that actin filament can move on the surface of the glass. The question is that if you add molecular glue, dendritic molecule with guanidine ions, what happens? So the motions are arrested entirely. The very important thing is that they still try to move. They're struggling, but their motions are totally arrested because of the adhesions. So here we have myosin, and then actin filaments. And if you add molecular glue, then these two protein units are connected together by this molecular glue. So the motions of actin filaments are arrested. The other new example I'd like to show you is a photochromic molecular glue. The difference is only here, okay? And the peripheral parts units are identical. So these are guanidine ions. Then what is the function of this core unit, so-called azobenzene in chemistry? Yes, azobenzene. So this unit is known to change its shape depending on photoirradiations. So initially, it adopts this type of shape, which we call transform. And then if you shine ultraviolet light to azobenzene, then the shape changes from trans to so-called cis. Yes, and cis. And if you just expose the cis form to visible light, then you come back to the transform. And you can repeat many times. Yes. So what we wanted to do with these molecules. So here we have a lipid bilayer membranes. And this is like an artificial cells, okay? And then if you try to make a distortion of lipid bilayer, then outside we have sodium hydroxide that can permeate through the lipid membrane, and then the pH of the interior environment is going up. Then in the inner part of the lipid membrane, we have a certain type of molecule that sense pH change by emitting light. So what we wanted to do is to do like this. Okay, we just make a distortion of lipids and hope that sodium hydroxide comes inside. And then this molecule can emit light. So this is a trick we utilize in order to, so this is a proof of concept type of work, and we will see what is happening. Actually, initially, we have this type of transform, and finally, upon photoirradiation, we end up with cis form. Then you see that the molecular structure changes from here to here, and this part adheres to the surface of the lipid membrane. And what happens if you just change the shape, then the lipid membrane just changed locations. And so the important keywords are adhesion and frictions. So what we did here is to irradiate the system with 365 nanometer light periodically to see what is happening in the fluorescence, luminescence from the molecules inside the vesicle. So as you can see from here, the luminescence from the molecule inside the lipid bilayer can go stepwise up, meaning that you can actually induce disordering of lipid barriers. So the conclusion here is that this molecule can perfectly serve as a glue in biological system. So in the course of this study, one of my students came to my office to say that sometimes he loses these compounds, particularly for spectroscopy. Then we discussed almost for 1 hour and finally noticed that this molecule can adhere to the surface of the glass for the measurement. And because if you take a look at the surface of the glass, and you see so many oxyanions, okay? So again, we can expect polyvalent interactions, multivalent interactions, then octopus are very happy to stay on the glass surface because of these multivalent interactions. So on the basis of this discussion with students, we came up with an idea to utilize this discovery for making material. And as a consequence of this, we decided to utilize clay nanosheets instead of glass. Clay nanosheets in combination with a new type of molecular glue, then we expect that we are able to make some materials in water. So let me tell a bit about clay nanosheets. So this is commercially available nanosheets we call laponite XLG. This is a disc-shaped nanoscale object. The average diameter is about 25 nanometer, and the thickness is 0.5 nanometer. And this has been utilized for cosmetic, many applications already, and it is totally non-toxic. And if you take a look at this open surface, I'd like to tell you that the open surface is full of negative charges like oxyanionic functionality. But on the other side, if you just come to the edge part of the disk, then you see positive charges because of the intercalation of sodium ions, other alkali metal ions. So one side is fully negative and the other side is positive. This is one of the character of laponite XLG. And we use this laponite XLG as 2% by weight making material. The other molecules, I'm sorry, because this chemistry, I'm sorry. But anyway, I like to tell a bit about molecules. It is very complicated, probably for you. Well, this is a new type of molecular glue. You can recognize the difference. Yes, so we call this as G3 binder. G3 means third generation denomer. Okay? So this molecule, again, has an guanidinium ions on the periphery and water soluble. The difference is that we have spacers in between two sticky units, dendron units, here. So in parentheses, we have repeating units, and the number of the repeating units is 250. So this spacer is very long, and the shape of this molecule is something like this. So there are two sticky parts which are connected by flexible spacers. So the important point is that we utilize this organic molecules only 0.2% by weight. So how we are able to make a very strong three-dimensional network structures? by using these two units. So initially, we just add clay nanosheets 2% into water. And because of the plus-minus characters, we just end up with suspension. It's not very difficult to make dispersion. This is not good, so we decided to add a very tiny amount of sodium polyanions. Okay, polyanion. This is once again commercially available, 0.05%. Then this polyanion can adhere to the edge part of the clay because edge part is full of positive charges, plus-minus interaction takes place, and then this interaction can destabilize the agglomerates, and you end up with dispersion here. So you have a transparent water. Then we add G3 binder here to finish up the three-dimensional network structure by adhering these sticky parts to the open surface of the clay. So you have this three-dimensional network structure, and you end up with gel. So this is the movie show how easy food preparation is. Laponite, water, laponite, and this is sodium polyacrylates and polyanion, commercially available. And this is main player G3 binder. Then water comes first, and the Dr. 1 is adding sodium polyacrylate 0.05%. He's a very unique person. He likes to use this vortex mixer. So every time he uses vortex, and then he's adding clay nanosheets, 2 8%. And again, he's very happy to use vortex. It's already finished, but okay. And then finally, he's going to add G3 binder. It's very tiny amount as a very dilute aqueous solutions. Yes, finished. He must be very unhappy. Okay, 3 seconds, you end up with gel. Gel is totally transparent, and you don't see any light scattering. Thank you very much. It's very easy, so anyone can make an aqua materials. Even my wife can make it. So aqua material is very unique. I'd like to tell a bit about the unique properties of aqua materials. It is mostly composed of water, so it is inflammable. The black substance you see is from this flame, not from the materials. So I'm sorry, this is showing kind of a rheological properties, but I like to tell you that if you go up, then meaning that your material is very strong. Okay, by changing the amount of clay from 2% up to 5%, just a 2.5 times higher here, but the mechanical properties go up tremendously. Okay, then 0.5 megapascal as the champion data so far, if you consider the hydrogels prepared by simple mixing. It's very strong. And some people are interested in utilizing a materials substance for making a gel from seawater. Unfortunately, at this moment, current version doesn't allow us to gel seawater, but up to a certain level of sodium chloride, then we have nice mechanical properties, but if the sodium chloride contents exceed this level, then the mechanical properties goes down because of the competition of the guanidinium ion clay interaction with salt. So one of the interesting aspects of these materials shown here, so we prepared here 25 degrees Celsius and aqua materials and cool it down to 10 degrees C and heat it up to 70 degrees C and cool it down to 25 degrees C. And once again, these represent mechanical properties. And important thing is that you don't see any change. So we are able to cool it down to -20. Still, the material is flexible. And you can heat it up to 100 degrees Celsius, but the materials still can maintain the same mechanical properties. And usually, for conventional hydrogels or organogels, if you heat it up, then you induce gel to solid transition. But in this particular case, all the events are kinetically trapped and out of an thermodynamic equilibrium, so that even though you heat it up to 120 degrees C, for example, no change takes place. Just water evaporation takes place. So this first prototype of second generation high molecular glue is designed for enzymatic hydrolysis because of the environmental issues. And once again, I'm sorry, this is a complicated chemistry, but so this particular linkage can be cleavable by enzyme. So if you would like to convert aqua materials back to water, only thing you can do is to cut these legs so that polyvalency is turned off. And as a consequence of this, materials return to water. And of course, you can cleave these units by acid and base. Here, just for the visibility, we just prepared a colored hydrogel. And on top of that, we added an acidic or alkaline waters. And in here, acidic, yes, and alkaline water. And in the middle, we add a very concentrated sodium chloride solutions or phosphate buffer to see what is happening to the gel. And under acidic conditions, in 48 hours, the gel started to be deteriorated because of the cleave of the ester linkages. And under alkaline conditions, this comes much earlier because the linkage is reactive with alkaline. The important point is that in the middle, you see that we have very concentrated sodium chloride or phosphate buffer, but you don't see any change. Well, this is one of the other interesting aspects of the gel. Here we apply strong shear force, like this, okay? Immediately, the materials just collapse to behave like water, quasi-water, quasi-solid, but stress. But as soon as you remove the stress, then the materials can recover the initial mechanical properties very rapidly, almost 3 seconds, and then you can repeat many times without any particular deterioration of the material. This type of property is very important. For example, if you just cover your car surface with this type of materials, you can avoid serious collision, because if you just have collision, then the material can absorb all shocks. Aqua material is adhesive in the freshly cut surface. Okay, here we have one piece of aqua materials which is cut into two pieces, and within 1 minute, if you just push these two pieces so that this freshly cut surface get into contact, okay, they emerged perfectly. So this is one of the very important aspects of current materials. So we call this as self-healing property or self-mending property. For the preparation of aqua materials, you don't have to heat, you don't have to cool. You just mix necessary components at room temperature in water. So one of the advantages of this aqua material is that you can incorporate an enzyme in aqua materials. Now the enzyme is portable, okay? So enzyme can live in aqua materials for a long time, and then even it can catalyze some organic reactions. Here we have prepared an aqua materials that contains myoglobin as an enzyme, and in the presence of hydrogen peroxide and this particular type of organic molecules, and if you just put this type of aqua materials, unique type of aqua materials into this aqueous solutions, then reaction takes place to form this colored materials, substance. What does it mean is that these substrates can go inside into the aqua materials and then have some reactions and go out, product can go out. So this reaction turns over many times because the myoglobin is mostly in the water environment. So if you just utilize simply clay or G3 binder, the clay case, the activity is almost identical to the native myoglobin. But in case of G3 binder, as you can imagine, that this G3 binder can adhere to the surface of myoglobin so that it deteriorates the catalytic activity. On the other hand, if you just put myoglobin into aqua materials, then the activity is very good, just 70% of native myoglobin. Then this is, I think, one of the interesting aspects of aqua materials, because myoglobin feel like it is in water. So I like to compare our aqua materials with other pioneering materials, hydrogels materials. The upper two are categorized into covalent hydrogels, where you have to do some chemistry for the preparations. So the required skill must be very high. These materials can be prepared only in the factory or in a laboratory. Well, and the other tools, lower tools, are categorized into supramolecular hydrogels, where you can prepare aqua materials, hydrogels by simple mixing. So the required skill must be very, very low. Anyone can make it. So if you take a look at the mechanical properties, for example, double network hydrogel invented by Professor Gon, it is tremendous, 70 megapascal, which we can afford by using supramolecular approach. Nanocomposite, 1 megapascal. And if you take a look at mechanical properties of oligoelectrolyte hydrogels or oligopeptide hydrogels, the mechanical properties are very, very small, so you can't make shape persistent materials. This is like a mayonnaise, okay? Well, so the organic contents, this is the lowest example of these, but organic contents is still very high. And here you can reduce the organic content to 3%, 1%, and as a consequence of it, you can increase the water contents. So there are many good points and bad points. This is, I would say, I'd like to introduce the work of Professor Gong because it is very interesting. I just get this movie from her, and now here we have a single network gel, and the other one is double network, and then we're going to compress. So this one is broken, and the other one is still okay. And if you just release, then it can recover the initial shape. They're perfect. So there are two polymers that can interdigit together to form this type of double network structures. No one can utilize, no one can happy to have this, but suppose that you utilize this as a golf ball, then the upper one can be totally okay. You can't expect a very good record, so unfortunate, but anyway. So nothing happens. It's a huge interesting mechanical properties. So this is the lever for us from a supramolecular approach. Some days we like to achieve this type of mechanical properties. This is a nanocomposite hydrogels. It is mostly like a lava. Okay. Yes. I'd like to introduce our example, aqua materials. Water content is 98% to 95%, depending on the contents of clay. Okay? So this material is mostly composed of water and inorganic entity. And organic content is only 0.2% altogether. And mechanical property is almost comparable to this covalent hydrogel, and self-healing capability is perfectly okay, and the required skill is very low. And finally, it can maintain its shape in organic solvents. So once again, here we have one piece of aqua materials, which is now put in ethylene glycol, which is organic solvent. And what happens? Within 3 hours or 4 hours, all the water molecules are replaced with ethylene glycol. Now we have organogel. Mechanical property is very good, but if you would like to prepare organogel directly from ethylene glycol and clay and our molecular glue, so you end up with precipitates of clay nanosheets. No hydrogel, no gel materials is formed. So you have to come through aqua materials up to organogel. The other one is more interesting because ion, liquid ion. So this is what we call ionic liquids. As you remember that we are not able to gelate seawater, but once you form an aqua materials and put it in this ionic liquids, what happens? Then the material can maintain perfectly the original shape, but all the water molecules are replaced with ionic liquids. Very interesting. Once you form three-dimensional network structures, then this network can tolerate in any condition, including salt liquids. Heart, always very important for us, but heart is sometimes broken like this. And what we did here is just to put it in a vacuum so that water molecules just gone. So what you see here is really a substance that supports heart shape. The interest question is that if this white stuff still remember what it was, then we put it back in water to see what is happening. Yes, you recover the heart shape perfectly, almost perfectly. So initially we thought that this white stuff, just forget what it was, because everything is supramolecular, non-covalent chemistry, non-connection chemistry, but it can actually remember the heart shape. So once again, the network structure once formed is almost infinite. Remember the connecting parts. So you understand that our aqua material is very unique compared with other pioneering examples. But still, double network is very attractive for us. So as a supramolecular chemist, I wanted to mimic some aspect of double network hydrogels by our system. So what you see here is three-dimensional network structures. And then we just suppose that we are incorporating just a polymer molecules within this porous structure to see what is happening. This could be like a double network one, but it is not a real one, just a pseudo double network. But anyway, we are very much interested in investigating the properties of this type of materials. So we are now here, clay, dispersed clay, and a monomer for making polymers. And there are two ways from our side to come up to this side, okay? First, we add G3 binder to finish up the three-dimensional structures. And pink, that's monomer. So if you just, for example, expose this gel to light, then you do photopolymerization, so you can connect these pink pearls to make polymers inside the gel. The other method, you do first the polymerization to form a polymer clay composite gel, which is very weak, unfortunate. But if you just expose this gel to G3 binder, then you end up with double network structures. So there are two ways for us to come up to this double network. And I'd like to just explain a bit about method one, okay? Here we have clay, which is dispersed in the presence of monomer, and so we add G3 binder to finish up three-dimensional structures. Then, expose to light, end up with double network. So this is the gel. So you see that this is the aqua lava. So the elastic properties are very enhanced, and you can stretch many times reversibly. And an interesting thing that if you stretch, then the materials just become opaque because they orient clay nanosheets macroscopically. Okay, this is clay contents 5%, and water is polymer contents 1.0, and all the other water. So this is the demonstration for method 2, okay? We prepared a single network with, first, this is very weak, and then we expose these materials to G3 binder so that G3 binder comes inside a gel to finish up the three-dimensional network structures. So battery is anyway. So just a demonstration, we prepared a rod shape, weak single network gel, and put it in a cylinder to form spiral structures, okay? Then we fill this cylinder with an aqueous solution containing our molecular glue to see what is happening. Of course, we expect that this spiral shape is memorized. Yes, it is perfectly memorized, and by using dendritic guanidine salt, then you can make a three-dimensional structure from 1D rod by doing so. And if you just utilize the pendants, guanidine ions, then you don't have any memory effect. So shape memory can be generated by the second supramolecular network structure in the materials. Well, this is one of the my final topics. And quite recently, we were able to align inorganic nanosheets in a parallel way. So you see that these inorganic nanosheets are perfectly oriented, parallel to one another. And what is the good advantage or interesting aspect of this is that, yes, if you just take a look at these materials from these directions, perfectly the materials are opaque. On the other hand, if you see the materials from this side, then you see that material is nearly transparent. And the same thing happens if you just take a look at the materials from the other side. So the important point is that the inorganic nanosheets align in very regularly over a macroscopic length scale. And the only thing you need to do is to expose these materials to magnetic field perfectly, and they are oriented. And there are some examples for this, but mostly you align these type of inorganic nanosheets parallel to the magnetic flux. But in this particular case, the magnetic flux comes that way, and then the sheets align orthogonally. So this is the first example, and only with the orthogonal orientation with magnetic flux, then we're able to make it. So, so you see that materials has a large optical anisotropy. One more thing I'd like to tell you is that this material shows a very large mechanical anisotropy, because I'd like to tell you that we have so many charges on these inorganic nanosheets. As you can imagine, the sheets can be repulsive to one another. So if you just push these materials from these directions, then the material can tolerate against the pressure. Okay? There's almost no deformation, or only a very small deformation by pushing this way. On the other hand, if you just push the materials from this side or that side, because there's no friction inside, then the material can deform very easily. So this unidirectional macroscopic orientation of repulsive and inorganic nanosheets is very important if you consider that this gel can be utilized for cartilage tissues. Okay? So we are very much interested in applying this type of materials for our some part of the body. Well, finally, in chemistry fields, so dendrimer is one of the beautiful molecules, but for synthesis, preparations, it is one of the tough molecules, and my students are always fascinated by these molecules, but within 2 weeks, they give up to synthesis. They start complaining something. Okay, so no one want to utilize dendrimers. And my good friend of mine Craig Hawker, University of California, Santa Barbara, provide us with a linear version of molecular glue. Now you see that the spacer part is here, almost identical. And this, this is very much like chemistry, but so number 7, meaning that we have 7 repeating units, and the other side you have 7 repeating units also. So this is the linear version of our dendritic molecular glues. So the interest is that if this linear version can also induce gelations or not. And the answer is, answer is that yes, it can form gels. But compared with a dendritic molecular glue, you have to be patient because the gelation takes place 30 minutes or 1 hour after you mix. So the molecular structure plays a very important role. And if you want to prepare the gel quickly, then only option is to utilize dendrimers. Dendrimer is like an optoglass, and it can very efficiently adhere to the surface of inorganic substance. So I'd like to sum up my talk by putting some interesting aspect of aqua material. It is mostly composed of water. It contains only 0.2% organic component and preparable easily and anywhere and anyone. So it is very good for example, in a hospital, even medical doctor or nurse can prepare aqua materials on site. And aqua materials could be disposable because it is designed for environmental friendly aspect and self-standing and self-repairable and transparent and non-flammable and adhesive and capable of containing bioactivities. And very finally, it is important now in Japan that it can shield neutron, the Fukushima issue. Okay, so and I hope in the future some parts of petrochemical could be replaced with water-based materials, and I think it is very important for realizing a sustainable society. Well, with these works, so we need, there are a couple people who just contribute a lot to the development of these technologies. And I appreciate some of the students that contribute a lot. And finally, thank you very much for your kind attentions. And once again, one introduction.
Thank you very much for that talk, which truly showed how creative a chemist can be. There will now be a pause while we will collect up questions, either about tonight's talk or more generally about the theme of the colloquium. And in a few minutes, the questions will be discussed by the speakers for this week. Thank you. Are these materials compatible with cells, for example, cell culture?
In principle, yes. We haven't yet checked that possibility, but so far we do, in different experiments, we utilize our molecular glue for cell transfection or something. And so far, we don't find any problems. And one good news is that one of the collaborators just checked the toxicity of a molecular glue, And they found that it is practically, it's below the required, level of the clinical usage. So we're very happy to know that our material is totally usable for this type of applications.
Several questions. What happens when the material is exposed to extreme heat?
Extreme heat?
Yeah, in a fire.
Yes. The clay serves as a boiling stone. So usually, evaporation of water takes place at 100 degrees Celsius, but our aqua material case, the evaporation starts at 80 degrees Celsius, much lower than ordinary temperature. But the evaporations is slower than ordinary hydrogels we compared. But in order to stop perfectly the evaporation, you need to coat our materials with some polymers, thin film polymers, films. And that's enough to stop the evaporations. And one of the interesting funny story that the first person who came to my office after we published this paper is the one from Tokyo Fire Office, and they are interested in utilizing our materials for fire issues. And particularly for tall buildings or high buildings, only thing you can do is to lift up the water by using helicopter, in Japan at least. And helicopter is not allowed to have an access to the building with, by 25 meters by law. So when they release water, then only 30% of water that hits the targets. But they expect that by using solid water, then 100% the solid water comes to the target, and then fire is going to be solved. This is the very ambitious applications.
Since we have a medical doctor, perhaps Rod could comment, could this be used to replace biological tissue?
I don't know enough about it, but it makes me wonder about a cartilage replacement, but that's just a guess. What do you think?
Yes, I think we have, that is a very promising applications. But so nothing started yet, so we have to check by experiments.
Because some materials, like certain cartilages, are actually polyanionic gel-like materials. So in a sense, they're kind of a biological analogy to what you're making synthetically.
Yes.
Yeah.
Yeah, really, totally.
Somebody wants to know if you could make a violin string or a guitar from this material.
It works only within 5 minutes because the evaporation takes place. If you go to a very thin string, then evaporation is faster.
So you have to play fast.
Yeah, you have to play fast.
Could you make the material harder for building purposes?
Yes. So mechanical properties are totally dependent on the amount of clay. And Laponite XLG is not a very good candidate for that because the 5% is something like a maximum. But Laponite XLS, featuring pyrophosphate with clay, then it is very dispersible. And in that case, we have to cleave the pyrophosphate structure. So you need to add a very small amount of acid. So sooner or later, the Laponite XLS just turn to Laponite XLG, and then so by doing so, you can increase the amount of clay. Yes.
Two questions here. Can you comment on how easy it is to make very large amounts, and how quickly do you think we'll see these materials on the market?
On the market. One of the big problem is that it's a dendrimers. It's a common problem for dendrimers because dendrimers plays a very important role in many aspects, but the synthesis is very tough. It is totally impractical. So good news is that, as I told you in the final part of my talk, my friends Clay Coker just provided us with a linear version, which is very easy. Just by doing ring opening polymerizations, you end up with ABA type of block copolymer, and that works perfectly if you don't consider, if you do not want to make gel very quickly. So after 1 hour, if you just put, stand gel at room temperature, then the mechanical properties are almost identical. But only thing is that you have to wait for 1 hour. Yeah. So it depends on the applications.
Can you eat it?
Eat?
Could you put flavors in the water and have a...
Probably guanidine ion gives you some bitter taste, so no one happy. At the market, because one of the chemical company in Japan would like to just now trying to do a scale-up synthesis of dendrimers, and also they already invented a second-generation aqua materials. We are not able to say publicly at this moment, but the second version could be much better and cheap and better. So I think that this can be on the market, but I'm afraid that our system is too expensive because of dendrimers.
We saw a lot yesterday about ions traveling through membranes. Can ions travel through aqua materials?
Yes. We checked. It is not giving a super performance, but if you align clay, then you have an isotropic conduction of ions, depending on the orientation clay. Yeah. This is one of the fundamental, the interesting points.
I think, here is one rather strange question. Some time ago, some Western scientists told us that water had a memory. And now your water materials do seem to have a memory.
Actually, in our system, water has no memory, but supporting stuff has a memory. So, and we are now, in collaboration basis, we're now checking if there is any particular structure in the trapped water inside the three-dimensional network structure. Yes, this is one of the interesting, work.
We heard yesterday that proteins have almost as much water inside, the crystals have almost as much water as your materials. Are they resistant or are they very weak crystals?
The protein crystals typically are much weaker because you've created strong electrostatic minus plus surfaces that really stick. Those same interactions are important in protein crystals, but they're not as there's not as high density of them. So they're much stronger in your designed system. And in your case, it's not a crystalline material, but some of the interactions are the same, but they're much stronger in your gel. Yeah. Right.
Particularly our system is very much dependent on clay property. And of course, we try to extend our system to a totally organic system by using, for example, tobacco mosaic virus or something as a counterpart of our dendrimers. But yes, we end up with a gel, but gel is very weak.
Could these be used to release pharmaceuticals slowly from a tablet of gel?
Yes, that's possible. But if there is any special interaction of pharmaceutical reagent with clay, then in that case, it's impossible. So hopefully, if we probably need neutral compounds. If there is any charges on these molecules, then we have some very strong electrostatic interactions. One thing is that we incorporate myoglobin into the aqua materials. And this aqua material can be put into water. And we don't find any release of myoglobin because myoglobin partly interact with clay, and then they are not allowed to release from that. So what we need is neutral compounds that have no special interaction with clay surface.
Could you use this for immobilizing enzymes?
Yes. One of the proof of concept work is the case of myoglobin, and we have two different ways of incorporating an enzyme or some other biological system into the gel. The method one is that you just put all things together to form gels. And the other one is that you just initially prepare aqua materials and then evaporate to have white stuff that is three-dimensional network. And then if you prepare some solutions that containing your molecules you want to incorporate, and then this dry gel is put into these solutions, then this solution just comes inside the three-dimensional network structures and it forms the gel. So by doing so, you are able to incorporate many different type of molecules or some for cosmetic stuffs or pharmaceutical stuffs, whatever. Yeah.
Perhaps I could ask the other members of the panel if there's anything they'd like to try with these materials.
I was wondering if you could, instead of the dendrimers, whether you could actually use hyperbranch polymers or to try and get the same effect, the same speedy onset. So hyperbranch polymers are a little bit like dendrimers, but they're not such a regular structure. So they're a compromise between dendrimers, which are perfect structures and highly branched, and the linear polymers, which are only have one group at each end. So there's a class of materials called hyperbranch polymers, which are some way between the two.
Yes, this is one of the very promising compromise. The only thing is that so the gel properties are very much dependent on the number of generation of dendrimers. We utilize G3, but if you just compare the properties of that with G2 or G1, then the mechanical property is very low. Even though you increase the amount of G2 or G1 much more, but you can realize the mechanical properties that's prepared with G3.
So that's quite surprising, as you said, that the linear polymer gives actually the same mechanical properties as the G3 dendrimer.
Yeah, so long as you have the same number of guanidine ions or even larger.
Okay.
Yeah. By linear opening polymerization, it's very easy to increase the number of guanidine ions because you just wait to at a certain point. Yeah.
Congratulations to Kuzo. It's very fascinating to coin a pun. You've just touched the tip of the waterberg, I think, not the iceberg. But it strikes me that you already talked about some limitations on what dendrimers you can use, but have you thought of other layered materials like a polyanion of graphene, for example, to use to organize into this cross-linked material?
Yes. Actually, we tried graphene oxide. Unfortunately, so far it doesn't work well.
One last question. Could you use these materials to store fuel? Because they would be resistant to shock and self-healing. make a fuel tank out of aqua material?
Yes. I have no answer at this moment. It's two big questions. Yeah.
Sounds like a Molotov cocktail.
Well, it would be what every child would like. You could make a glass that you could drop, break, and repair before your parents come home.
That's a good idea.
Okay, I think we have covered almost all the questions, so thank you for your questions, thank you for coming, and thank you especially to Takuzo.
Thank you very much.